pulsars, lighthouses of the universe beating with perfect rhythm. Right now, at this very moment, something extraordinary is happening about 1,000 light years from where you are sitting. A dead star, no wider than a mid-sized city, is spinning 11 times every single second. With each rotation, it sweeps twin beams of radiation across the cosmos, like the world's most powerful lighthouse. And those beams are so precisely timed that they put the best atomic clocks ever built by human hands to shame. This object has been performing this act without interruption for more than 10,000 years. It has never missed a beat, not once. And that is not even close to the most extreme example. There is another dead star out there, buried deep inside a crowded swarm of ancient suns roughly 28,000 light years away. That spins not 11 times a second, but 716 times a second. Think about that for a moment. 716 full rotations every single second. The surface of this star is moving at roughly 1/4 the speed of light. If you could somehow stand on its equator, you would be whipped around at more than 43,000 miles per second. A kitchen blender at full speed completes maybe 250 to 500 rotations per second. This star beats every blender on Earth, and it does so while containing more mass than our entire sun. Crushed down into a ball you could comfortably drive across in about 10 minutes. These objects are called pulsars, and they are among the strangest, most extreme, and most useful things the universe has ever produced. They are the compressed corpses of once massive stars, so dense that a single teaspoon of their material would weigh somewhere around 1 billion tons on Earth. Their magnetic fields are trillions of times stronger than our planet's. Their gravity is so severe that if you could drop something onto their surface from a height of 1 meter, it would hit with the energy of a thermonuclear weapon. And despite all of this violence, all of this extremity, they beat with a rhythm so perfect that scientists have used them to detect ripples in the fabric of space and time itself, to discover the very first planets ever found beyond our solar system, and to prove that Albert Einstein was right about things he could never have tested in his own lifetime. Pulsars are cosmic lighthouses, precision instruments, gravitational wave detectors, laboratories for physics beyond anything achievable on Earth, and tombstones marking the graves of stars that died in spectacular fashion. Their story begins not with some grand theoretical prediction or a carefully planned experiment, but with a young graduate student in England, a homemade radio telescope built from wire and wooden posts, and a tiny smudge on a paper chart that almost got thrown away. This is the story of pulsars, from their accidental discovery to the frontiers of modern physics. It is a story about what happens when stars die, about matter squeezed to impossible densities, about magnetic fields that bend the rules of reality, about clocks that keep time better than anything humans have ever engineered, and about how these bizarre remnants of stellar death have become some of the most powerful tools we possess for understanding the deepest secrets of the universe. And it all started with a bit of scruff on a piece of paper. The year was 1967. The space race was in full swing. Astronauts were preparing for what would soon become humanity's first steps on the moon. The Beatles had just released SGT, Pepper's Lonely Hearts Club Band. The Cold War cast a long shadow over scientific collaboration. And yet, in quiet corners of the world, researchers were pushing the boundaries of what we knew about the universe with little more than determination, clever engineering, and a willingness to get their hands dirty. In a muddy field just outside Cambridge, England, at the Mullard Radio Astronomy Observatory, a 24-year-old graduate student named Jocelyn Bell was doing something that did not look much like cutting-edge astronomy. For the better part of 2 years, she had been helping to build a radio telescope. And this was not the kind of sleek, gleaming dish you might picture when someone says the word telescope. This thing looked more like a farmer's fence gone horribly wrong. It consisted of more than 1,000 wooden posts, connected by over 120 miles of wire and cable, spread out over nearly 5 acres of countryside. It was designed to detect a phenomenon called interplanetary scintillation, the way that the solar wind causes the signals from distant quasars to twinkle. And it had been conceived by Bell's thesis advisor, Anthony Hewish. Bell had helped sledgehammer posts into the ground, solder connections, and string wire until her hands ached. When she arrived at Cambridge, she had been one of the very few women studying astronomy there, and she faced the kind of dismissiveness and hostility that was depressingly common for women in science at that time. Male students had stomped their feet and catcalled when she entered lecture halls. But Bell was made of stern stuff. She had grown up near the Armagh Observatory in Northern Ireland, where her father, an architect who had helped design the facility, had nurtured her interest in science from an early age. She had read Fred Hoyle's book, Frontiers of Astronomy, as a teenager, and had known since then that she wanted to understand the cosmos. When the telescope was finally switched on in July of 1967, it became Bell's job to operate it and to analyze the data it produced. And the data was not digital. It came out on rolls of chart paper, enormous curling ribbons of it, roughly 400 feet every single day, over a period of 6 months. Bell would analyze more than 3 miles of these paper charts, running them through her hands inch by inch, training her eyes to distinguish the sharp, twinkling signatures of quasars from the interference produced by human technology and from the natural noise of the sky. It was painstaking, tedious work, the kind of task that would cause most people's eyes to glaze over within the first hour. But Bell had an extraordinary eye for detail and a quality that turned out to be more important than any sophisticated instrument. She paid attention to things that did not fit. In August of that year, she noticed something peculiar. It was a tiny smudge, a bit of what she would later call scruff on the chart paper. It occupied less than 1/4 of an inch on the roll. Most people would have ignored it entirely. It looked like interference, like noise, like nothing at all. The telescope picked up all sorts of spurious signals, from car ignition systems to poorly shielded electronic equipment. And this little squiggle could easily have been one more piece of worthless static, but something about it nagged at Bell. It kept appearing at the same position in the sky, drifting across the same region of space, with the same timing that the stars followed. Whatever was producing this signal, it was rising and setting with the stars, not with anything on the ground. It was cosmological, not terrestrial. Bell flagged it with a question mark and moved on, but she kept watching, and the scruff kept appearing. She mentioned it to Hewish, who was initially skeptical. Interference seemed the most likely explanation. But Bell was persistent, and by late November, she convinced Hewish to let her use a faster chart recorder to get a better look at the signal. On November 28, 1967, the faster recorder captured something extraordinary. The scruff resolved itself into a series of sharp, regular pulses, arriving like clockwork every 1.337 seconds. The signal was astonishingly precise. Nothing in nature was supposed to behave like this. Stars did not pulse with this kind of mechanical regularity. Satellites did not produce signals like this. Variable stars, which do change brightness periodically, do so on timescales of hours, days, or weeks, not fractions of a second. The only explanation that seemed to fit, at least at first, was that the signal was artificial. Someone or something was broadcasting. For a few electric weeks, Bell and Hewish entertained the possibility, half jokingly and half seriously, that they had detected a signal from an extraterrestrial civilization. They labeled the source LG-M-1, which stood for Little Green Men. Hewish called meetings with senior colleagues, meetings to which Bell, as a mere graduate student, was not always invited. The implications of an alien signal were so enormous, so potentially destabilizing to the world, that there was genuine discussion about whether the discovery should even be published. But Bell herself was skeptical of the alien interpretation. She had been tracking this source for months, and it always appeared from the same point in the sky, rising and setting with the stars. If it were aliens broadcasting intentionally toward Earth, why would the signal show no variation, no modulation, no sign of information content at all? It was too simple, too repetitive, too much like a natural clock, and too little like a message, as Bell herself would later recall. She knew it was not artificial because she had been watching this thing for weeks, and it behaved exactly like a distant, fixed source in the sky. And then, shortly before Christmas, working late in the observatory while others prepared for the holidays, Bell found a second source, pulsing from an entirely different part of the sky with a different period. Then a third, then a fourth. The Little Green Men hypothesis collapsed. It was wildly improbable that multiple alien civilizations in different parts of the galaxy had all independently decided to broadcast featureless, rhythmic radio signals toward Earth, each at a slightly different frequency. Whatever was producing these pulses was a natural phenomenon, and it was apparently common. In February of 1968, Bell and Hewish, along with 3 other collaborators, published their findings in the journal Nature. The paper described the first 4 pulsating radio sources ever detected. Bell was listed as the second author on the paper. The objects would soon come to be known as pulsars, a contraction of pulsating radio source. The announcement sent shockwaves through the astronomical community. Theorists immediately set to work trying to explain what could produce such rapid, regular pulses. And within months, 2 physicists, Thomas Gold and Franco Passini, independently figured out the answer. Remarkably, Passini had actually predicted, before the discovery, that rapidly rotating, strongly magnetized neutron stars should emit radiation. The pulses were coming from rapidly rotating neutron stars, objects that had been predicted theoretically in 1934 by Walter Baade and Fritz Zwicky, but never observed. Objects so extreme that many physicists had doubted they could actually exist in nature. For this discovery, the 1974 Nobel Prize in Physics was awarded to Anthony Hewish and Martin Ryle. The head of the Cambridge Radio Astronomy Group, Jocelyn Bell, the person who actually noticed the signal, who built the telescope with her own hands, who analyzed 3 miles of chart paper over 6 months, who flagged the anomaly and pushed for follow-up observations when her supervisor wanted to dismiss it as interference, who found the second, third, and fourth sources that ruled out the alien hypothesis, was not included in the award. The omissions sparked controversy that continues to this day. The astronomer Fred Hoyle publicly and loudly protested her exclusion. Fellow scientists called it the Nobel Prize. The controversy became a touchstone in conversations about how scientific credit is allocated, particularly for women and members of underrepresented groups. Bell herself has been remarkably gracious about the whole affair for over 50 years, saying publicly in 1977 that she believed it would have demeaned the Nobel Prize to award it to a research student. Many in the scientific community have never agreed with that assessment, but Bell has always taken the high road, channeling her energy into a distinguished career in astrophysics and into advocacy for inclusion in science. In 2018, more than 50 years after her discovery, Bell was awarded the Special Breakthrough Prize in Fundamental Physics, worth $3 million. She donated every penny of it to a fund established through the Institute of Physics to help women, ethnic minorities, and refugees become research physicists. Her discovery, that little bit of scruff on a paper chart, that quarter-inch anomaly on a 400-foot roll of chart paper, turned out to be one of the most consequential findings in the history of astronomy. But to understand why pulsars matter so much, you first have to understand what they are. And to understand what they are, you have to understand what happens when a massive star reaches the end of its life. The death of giants, how pulsars are born stars are, in a fundamental sense, engines of balance. Throughout their lives, they exist in a delicate equilibrium between two opposing forces that are locked in an endless tug of war. Gravity, the relentless inward pull of their own enormous mass, tries constantly to crush them. And radiation pressure, the outward push generated by the ferocious nuclear fusion reactions burning in their cores, pushes back with equal determination. For millions or billions of years, depending on the star's size, these two forces hold each other in check, and the star shines steadily and stably, a beacon of light in the void. But this balance cannot last forever. Stars are burning through a finite supply of nuclear fuel. And for the most massive stars, those born with at least 8 to 10 times the mass of our sun, the end game is dramatic and violent. These heavyweights burn through their hydrogen supply relatively quickly, in perhaps 10 to 20 million years, a mere blink of an eye in cosmic terms. When the hydrogen in the core runs out, the core contracts, heats up, and begins fusing helium into carbon and oxygen. When the helium runs out, the star moves on to fusing carbon, then neon, then oxygen, then silicon. Each successive fuel ignites at higher temperatures and pressures, and each burns faster than the last. The timescales are dizzying. A massive star might spend 10 million years burning hydrogen, 1 million years burning helium, 1,000 years burning carbon, a year burning oxygen, and just a single day burning silicon, the star develops a layered structure like an onion, with progressively heavier elements being fused in progressively deeper shells, each burning more desperately than the last. And silicon fusion produces iron. This is where the music stops. Iron is the end of the line for nuclear fusion. It sits at the peak of the binding energy curve, which means that fusing iron nuclei together does not release energy. It absorbs energy. Every element lighter than iron can release energy through fusion. Every element heavier than iron can only be created by pumping energy in. When the core of a massive star has been converted to iron, it has built itself a dead end, a coffin of its own making. There is no more fuel to burn, no more outward pressure to generate, and nothing left to hold gravity at bay. What happens next unfolds with terrifying speed. The iron core, which at this point contains roughly 1.5 times the mass of our sun packed into a volume about the size of the Earth, is supported against gravity only by the quantum mechanical pressure of electrons, a phenomenon called electron degeneracy pressure. But as more silicon ash piles onto the core's mass exceeds a critical threshold known as the Chandrasekhar limit, roughly 1.4 solar masses. At this point, electron degeneracy pressure fails catastrophically. Gravity wins, and the core collapses. The implosion takes roughly 1/4 of a second. 1/4 of a second to compress more mass than the sun from something the size of Earth down to something the size of a city. The core falls inward at speeds reaching 1/4 of the speed of light. Temperatures spike to tens of billions of degrees, hotter than the center of the sun by a factor of thousands. The tremendous pressure forces protons and electrons to merge through a process called electron capture, creating neutrons and releasing a deluge of ghostly, nearly massless particles called neutrinos. These neutrinos carry away an almost inconceivable amount of energy. In about 10 seconds, the collapsing core releases roughly 100 times more energy than our sun will produce over its entire 10 billion year lifetime. And the vast majority of that energy, roughly 99%, is carried away by neutrinos. The remaining 1% is what powers the explosion itself, the supernova. And even that 1% is enough to briefly outshine an entire galaxy. The outer layers of the star, still falling inward because they have not yet felt the shock wave from the core bounce, slam into the newly formed neutron core at tens of thousands of miles per second and rebound. The exact mechanism by which this rebound converts into a successful explosion is still not entirely understood, and it remains one of the most active areas of research in computational astrophysics. Computer simulations of core collapse supernovae are among the most demanding calculations in all of science, requiring months of time on the world's fastest supercomputers to model just a few seconds of the explosion. But the basic picture is clear. The rebound, powered by the energy deposited by the neutrinos and the sheer violence of the collision, tears the star apart from the inside out. The explosion that follows is one of the most powerful events in the entire universe. For a few weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of stars. The blast wave hurls the star's outer layers into space at thousands of miles per second, seeding the cosmos with heavy elements. The The calcium in your bones, the iron in your blood, the oxygen you are breathing, the carbon in every cell of your body. All of it was forged in the hearts of massive stars, or in the crucible of their explosions, and scattered through space by supernovae. You are, in the most literal and physical sense, made of star stuff. And pulsars are the tombstones that mark the origins of that material. But while the outer layers are being flung into space, painting the cosmos with the raw materials for future planets and people, the core remains behind. And what remains is something unlike anything else in the known universe. All that matter, more mass than our entire sun, has been compressed into a sphere roughly 12 to 15 miles in diameter. That is about the distance from one side of a mid-sized city to the other. Picture the island of Manhattan. Now picture it containing more mass than the sun. If you placed a neutron star next to Earth, it would be a nearly invisible speck, but it would outweigh our planet by a factor of hundreds of thousands. This is a neutron star, and everything about it is extreme. The compression is almost beyond imagination. A neutron star's overall density is comparable to the density of an atomic nucleus, roughly 230 trillion times denser than water. A single teaspoon of neutron star material would weigh somewhere in the neighborhood of 5.5 trillion kilograms, which is roughly 900 times the mass of the Great Pyramid of Giza. If you could somehow scoop up a sugar cube-sized piece and bring it to Earth, you could not hold it. It would weigh more than a mountain. It would fall through your hand, through the floor, through the bedrock beneath the floor, and keep falling straight through the Earth. The gravity on the surface of a neutron star is roughly 200 billion times stronger than Earth's gravity. A person standing on its surface would weigh roughly 20 trillion pounds. If you dropped an object from a height of 1 meter above the surface, it would hit at about half the speed of light, and the impact energy would be comparable to a small nuclear detonation. These are not places where anything survives, including the atoms that make up ordinary matter. And here is where the physics of the collapse produces the two properties that transform this dead stellar remnant into a pulsar: extreme rotation and an extreme magnetic field. When the core collapsed from something the size of Earth down to something the size of a city, the conservation of angular momentum kicked in with a vengeance. This is the same principle that makes an ice skater spin faster when they pull their arms into their body. The original star might have been rotating slowly, perhaps once every few weeks or months, but it was enormous, hundreds of thousands or millions of miles across. When all that mass collapsed from a volume spanning millions of miles down to a sphere just 12 or 15 miles wide, the rotation rate increased by a staggering factor. A star that rotated once a month could, upon collapsing, find itself rotating many times per second. Young neutron stars are thought to be born spinning incredibly rapidly, perhaps hundreds of times per second. At the same time, the star's magnetic field was amplified to breathtaking levels. Just as the rotation rate increases when the star shrinks, because angular momentum must be conserved, the magnetic field is compressed and concentrated because the magnetic flux. The total amount of magnetic field threading through the star's surface is also approximately conserved. A typical star might have a magnetic field a few times stronger than Earth's, spread over an enormous surface area. When that star collapses to a fraction of its former size, that same magnetic flux is concentrated into a surface area billions of times smaller. The result is a magnetic field that can reach 1 trillion Gauss or more, trillions of times stronger than Earth's magnetic field, and millions of times stronger than the most powerful magnets humans have ever built. Take a rapidly spinning, city-sized ball of matter denser than an atomic nucleus. Wrap it in one of the most powerful magnetic fields in the observable universe, and you have the recipe for a pulsar. The lighthouse in the dark. Why pulsars pulse? The answer to why pulsars appear to pulse comes down to geometry, and it is surprisingly elegant. A neutron star's magnetic field is extraordinarily strong, and like the magnetic field of the Earth, it has a north pole and a south pole. But just like Earth's magnetic field, the magnetic axis of a neutron star is not necessarily aligned with its rotational axis. On our planet, the magnetic north pole is offset from the geographic north pole by about 11 degrees, which is why your compass does not point precisely to the true geographic north. On a neutron star, the misalignment between the magnetic axis and the rotational axis can be much larger, sometimes 10 degrees, sometimes 30, sometimes approaching 90 degrees. The two axes can be oriented at essentially any angle to each other. This misalignment is the key to everything. The intense magnetic field of a neutron star creates a magnetosphere, a region of space dominated by the star's magnetic influence that extends far beyond the physical surface of the star. Charged particles, electrons and positrons, are trapped by this field and forced to flow along the magnetic field lines. Near the magnetic poles, the field lines open outward, forming funnel-shaped regions where particles can escape the star's magnetic grip. As these particles are accelerated along the curved field lines near the poles, they reach extreme energies, approaching the speed of light, and they emit powerful beams of electromagnetic radiation through a process related to what physicists call curvature radiation and synchrotron radiation. These beams of energy shoot out from the magnetic poles like cosmic spotlights. Now, because the magnetic poles are not aligned with the rotation axis, as the neutron star spins, those beams sweep through space. The path they trace is a cone, much like the rotating beam of a lighthouse. If you are standing on a distant shore watching a lighthouse at night, you see a flash of light each time the beam sweeps past your eyes, even though the light itself is shining continuously. From your perspective, the light appears to blink on and off. The same thing happens with a pulsar. We, here on Earth, see a brief pulse of radiation each time one of the pulsar's beams sweeps across our line of sight. Even though the beams themselves are shining constantly, the pulsar does not actually turn on and off. It only appears to pulse because of the geometry of the rotating beam. This is the lighthouse model of pulsar emission, and it explains the remarkable regularity of pulsar signals with beautiful simplicity. The pulse period is simply the rotation period of the neutron star. When Jocelyn Bell detected a pulse every 1.337 seconds from that first source in 1967, she was measuring the rotation rate of a neutron star located in the constellation Vulpecula. Roughly 1,000 light-years from Earth, the star was completing one full rotation every 1.337 seconds, with mechanical precision that no human-built clock of the era could match. The radiation emitted by pulsars spans a huge range of the electromagnetic spectrum. Many pulsars are strongest at radio wavelengths, which is why they were first discovered by radio telescopes. But they can also emit visible light, ultraviolet radiation, X-rays, and even gamma rays. The specific mix of wavelengths depends on the energy of the particles being accelerated near the magnetic poles and on the detailed physics of the emission process, which, even after more than 50 years of study, is not fully understood. The exact mechanism by which pulsars generate their radio emission remains one of the most persistent unsolved problems in astrophysics. We know the broad outlines: rapidly rotating magnetic field, accelerated particles, and beamed radiation. But the details of how the radio waves are produced are still debated. What we do know is that this emission is not free. The energy that powers the beams has to come from somewhere, and it comes from the rotation of the neutron star itself. The rotating magnetic field acts like a brake, converting the star's kinetic rotational energy into electromagnetic radiation and flinging it into space. With each rotation, a tiny amount of rotational energy is lost. This means that pulsars are gradually slowing down. The braking effect is subtle for most pulsars, typically amounting to a loss of perhaps a trillionth of a second per second for older pulsars, but it is measurable with precise timing, and it is relentless. Over millions of years, pulsars gradually spin down. Their beams weaken. The voltage drop that accelerates particles near the poles diminishes, and eventually, the pulsar crosses what astronomers call the death line, the threshold below which the emission mechanism can no longer operate efficiently enough to produce detectable radiation. At that point, the pulsar goes dark and becomes just another invisible neutron star drifting through the galaxy, still spinning, but no longer broadcasting. For a typical pulsar, this journey from birth to darkness takes somewhere between 10 million and 100 million years, given that neutron stars have been forming throughout the entire 13.8 billion year history of the universe. This means that the vast majority, estimated at roughly 99%, of all the neutron stars ever born have already crossed the death line. The pulsars we can observe today are the relatively young ones, the still vibrant remnants of comparatively recent stellar explosions. Billions of old, dead pulsars drift silently through the galaxy around us, invisible and undetectable, their broadcasting days long over. But there is an important exception to this rule, a class of pulsars that seem to cheat death entirely. Cosmic clocks, the astonishing precision of millisecond pulsars. In 1982, a team of astronomers led by Don Backer at the University of California, Berkeley, made a discovery that stunned the pulsar community. They found a pulsar that was spinning at the almost unbelievable rate of 642 rotations per second. This was wildly faster than any pulsar found up to that point, and it seemed to make no sense. How could a neutron star, a dead stellar remnant that should be gradually slowing down over time, be spinning so incredibly fast? The answer turned out to be one of the most elegant pieces of astrophysical recycling in nature. Some neutron stars exist in binary systems, orbiting a companion star. For most of the binary's life, the two stars might orbit each other without much interaction, but many stars swell up enormously as they age, ballooning into red giants that can engulf the space around them. If the companion star swells up enough, its outer layers can overflow the gravitational boundary between the two stars, a region called the Roche lobe, and material begins to stream from the companion onto the neutron star. This infalling material does not drop straight down. It carries angular momentum with it, inherited from the companion star's orbital motion. And as it spirals down onto the neutron star's surface, it forms a swirling accretion disk. The accumulated angular momentum of this infalling material gradually spins the neutron star back up, like a cosmic hand pushing a merry-go-round. Over tens of millions to hundreds of millions of years, this process, known as recycling, can accelerate the neutron star from a slow spin to hundreds of rotations per second, far faster than when it was born. The accretion process also has another important effect. It buries and weakens the neutron star's magnetic field. The mechanism is not entirely understood, but it is believed that the infalling material creates electric currents that partially screen the original magnetic field, reducing its strength by factors of 1,000 to 10,000. This is critical because a weaker magnetic field means less braking torque, which means the pulsar slows down much more gradually after the accretion phase ends. A millisecond pulsar can continue spinning for billions of years, essentially forever on human timescales, without crossing the death line. This makes millisecond pulsars some of the oldest known pulsars in the galaxy, ancient objects that have been spinning since before our solar system even existed. These cannibalistic pulsars have been given colorful nicknames, systems where the pulsar is actively destroying its companion, stripping away its mass through intense radiation and particle winds, are called black widow pulsars or redback pulsars, named after species of spiders known for devouring their mates. In these systems, the companion star is being slowly whittled away, its material either accreted by the pulsar or blown off into space, until eventually nothing remains but the pulsar itself, spinning in solitary splendor, its companion consumed. The current record holder for the fastest spinning pulsar is an object with the catalog designation PSR J17482446 discovered in 2004 by Jason Hessels of McGill University and his colleagues using the Green Bank Telescope in West Virginia. This pulsar sits inside a globular cluster called Terzan 5, a dense ball of ancient stars located roughly 28,000 light-years away in the direction of the constellation Sagittarius. It spins 716 times every second, which works out to nearly 43,000 revolutions per minute. At that rotation rate, the equator of the neutron star is moving at roughly 25% of the speed of light. If the star were spinning even slightly faster, the centrifugal force at its equator would overcome the star's own immense gravity, and material would be torn from the surface and flung into space. Theorists calculate that the absolute maximum spin rate for a neutron star, before it literally flies apart, is around 1,200 rotations per second. So the fastest known pulsar is already at about 60% of this theoretical maximum. the second fastest known pulsar, PSR J900 and 52-607, spins at 707 rotations per second, and was discovered in 2018 using a Dutch radio telescope array called LOFAR. This pulsar is a black widow, actively consuming its companion star, and its discovery hints that the fastest pulsars might be preferentially found at low radio frequencies, suggesting that an entire population of ultra-fast pulsars could be hiding undiscovered because previous surveys were not sensitive to their steep radio spectra. But speed alone is not what makes millisecond pulsars so scientifically valuable. The truly extraordinary thing about them is their stability as timekeepers. The pulses from a millisecond pulsar arrive with a regularity that rivals, and in some cases exceeds, the precision of the best atomic clocks on Earth. The timing stability of the best millisecond pulsars has been measured to a precision of better than 1 microsecond over a decade. That means the pulsar's rotation rate is stable to roughly 1 part in 10 trillion or better. To put this in perspective, imagine a clock so precise that it would not gain or lose a single second in more than 30 million years. That is the kind of timekeeping precision that millisecond pulsars achieve, not through any engineered mechanism, not through any careful calibration or maintenance, but simply as a consequence of having an enormous amount of angular momentum concentrated in a tiny, nearly frictionless ball spinning in the vacuum of space. They are, in a meaningful sense, the most perfect natural clocks in the universe. This extraordinary precision is what has transformed pulsars from mere astronomical curiosities into some of the most powerful scientific instruments in all of physics. The guest star, a 1,000-year-old supernova, and the Crab pulsar on July 4th in the year 1054, during the reign of Emperor Renzong of the Song dynasty. Chinese astronomers at the imperial court made a careful note in their official records. They had observed the sudden appearance of what they called a guest star, a new and brilliantly bright point of light in the sky near the star we now call Zeta Tauri, in the constellation Taurus the Bull. This was no ordinary star. It was so bright that it could be seen in broad daylight for 23 days, blazing away in the blue sky as if it demanded to be noticed. At night, it was the second brightest object in the heavens, outshone only by the moon. Japanese astronomers recorded it as well, noting its brilliant yellow color. Chroniclers in the Islamic world documented the event, and there is even evidence, in the form of a pictograph found near the Peñasco Blanco site in Chaco Canyon, New Mexico, that the ancestral Puebloan people of the American Southwest depicted the event in rock art, a crescent moon adjacent to a bright star, painted on a stone overhang, in roughly the correct position relative to the constellation where the guest star appeared. The guest star remained visible to the naked eye for 653 days, nearly 2 years, before finally fading from sight. Then it disappeared into history. For centuries, no one in the Western world connected these ancient records to anything in the modern sky. But in the early 20th century, astronomers noticed that an expanding cloud of glowing gas in the constellation Taurus, a fuzzy patch that had been catalogued as Messier 1, or MOAN, the very first entry in Charles Messier's famous catalogue of nebulous objects, was getting larger. The English physician and amateur astronomer John Bevis had first noticed the nebula around 1731. Charles Messier had independently spotted it in 1758 and mistakenly thought it was Halley's comet, an error that frustrated him so much he began compiling his famous catalog, specifically to avoid similar confusion in the future. In the 1920s, astronomers Carl Lampland and John Charles Duncan independently discovered that the nebula was expanding. By tracing this expansion backward in time, using the rate at which the gas was moving outward, they could estimate when the explosion occurred. The date they arrived at matched beautifully with the records of the Chinese, Japanese, and Arab astronomers from 1054. The guest star had been a supernova, the violent death of a massive star roughly 6,500 light-years from Earth. The expanding debris from that explosion is what we now call the Crab Nebula, and it is one of the most intensely studied objects in all of astronomy. Roughly 10 light-years across, and still expanding at more than 900 miles per second, it glows with the combined light of 75,000 suns. But what powers it? A supernova explosion is a one-time event. The initial blast, no matter how powerful, should have faded long ago. After nearly 1,000 years, the debris should have cooled, slowed, and darkened. Something must be continually pumping enormous amounts of energy into the nebula to keep it shining so brightly. The answer was found in the late 1960s when astronomers discovered a pulsar sitting right at the heart of the Crab Nebula. The Crab pulsar spins 30 times every second and emits radiation across the entire electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. It is one of the youngest known pulsars, born in the very same supernova that Chinese astronomers witnessed nearly 1,000 years ago. And it is still enormously energetic. The rapidly spinning magnetic field of the Crab pulsar accelerates charged particles to nearly the speed of light and flings them out into the surrounding nebula. These high-energy particles slam into the slower-moving gas ejected by the supernova, energizing it through a process called synchrotron radiation and causing the nebula to glow brilliantly at wavelengths spanning the entire electromagnetic spectrum. The pulsar is literally keeping the Crab Nebula alive, feeding it energy rotation after rotation, year after year, century after century. Without the pulsar at its heart, the Crab Nebula would have faded into darkness long ago. But this cosmic power station runs on its own rotation, and every bit of energy it pumps into the nebula is energy stolen from its spin. The Crab pulsar is slowing down, losing about 38 billionths of a second per day. Over decades and centuries, this adds up. The pulsar, for which Chinese astronomers unknowingly created the birth announcement, will eventually slow below the death line. Perhaps tens of millions of years from now, the nebula will fade, the pulsar will go silent, and all that will remain will be a dark neutron star drifting through space, its millennial performance finally over. Gravity's messengers, how pulsars proved Einstein right and heard the cosmos hum. In the summer of 1974, a graduate student named Russell Hulse was conducting a systematic survey of the sky using the enormous 300-meter radio dish at the Arecibo Observatory in Puerto Rico. Hulse was working under the supervision of Joseph Taylor, a physicist at the University of Massachusetts, who had the foresight to recognize that a careful, sensitive pulsar survey could turn up objects of extraordinary scientific value. Taylor had designed an efficient computational search algorithm that could sift through the radio data and identify the telltale periodic signatures of pulsars far more effectively than previous methods. Hulse was operating the telescope and processing the data, scanning the sky strip by strip. Among the dozens of pulsars Hulse detected was one designated PSR B1913+16. At first, it seemed like a fairly typical pulsar, spinning about 17 times per second with a period of 59 milliseconds. But as Hulse carefully timed its pulses over a period of days, he noticed something peculiar. The pulse period was not constant. It varied systematically, sometimes arriving slightly earlier than expected, sometimes slightly later, and the variation repeated on a cycle of about 7 hours and 45 minutes. The pattern was unmistakable. The pulsar was in orbit around another object, and the changing pulse timing was caused by the Doppler effect. When the pulsar was moving toward Earth in its orbit, the pulses arrived slightly faster. When it was moving away, they arrived slightly slower. Hulse had discovered the first binary pulsar, a pulsar locked in a tight orbital embrace with a companion that turned out to be another neutron star. The two objects, each containing roughly 1 4/10 times the mass of the Sun, were orbiting each other at tremendous speed, separated by a distance comparable to the distance between the Earth and the Moon, completing one full orbit every 7 hours and 45 minutes. The maximum orbital velocity exceeded 300 kilometers per second, roughly 1,000th of the speed of light. This system was a relativistic laboratory beyond anything physicists had ever had access to before. The gravitational fields were so strong, the velocities so high, and the orbital parameters so precisely measurable thanks to the pulsar's clock-like pulses, that this system provided an opportunity to test Einstein's general theory of relativity in conditions far more extreme than anything available in our solar system. Taylor and Hulse immediately began a meticulous, years-long campaign of timing observations, and the results were spectacular. The system exhibited 3 distinct relativistic effects, all predicted by Einstein's theory, and all beautifully confirmed by the data. First, time dilation. When the pulsar dipped closest to its companion, moving deepest into the companion's gravitational well, the pulses slowed down slightly, stretched by the warping of spacetime, exactly as general relativity predicted. Second, the orbit itself was precessing, meaning the entire elliptical path of the pulsar was slowly rotating in space. The rate of this advance was 4.2 degrees per year, an enormous value compared to the precession of Mercury's orbit around the Sun, which had been one of the key early tests of general relativity. Mercury precesses by a mere 43 arcseconds per century. The Hulse-Taylor binary was precessing thousands of times faster, a direct consequence of the much stronger gravitational fields involved. But the third effect was the most profound of all. Over years of observation, Taylor and his colleague Joel Weisberg found that the orbital period of the system was gradually decreasing. The two neutron stars were spiraling closer together, losing orbital energy, and the rate at which this was happening matched the prediction of general relativity to within a fraction of a percent. According to Einstein's theory, two massive objects orbiting each other should radiate gravitational waves, ripples in the fabric of space-time that carry energy away from the system. As energy is radiated away, the orbit shrinks and the orbital period decreases. The observed rate of orbital decay matched Einstein's prediction to within 0.3%. A stunning confirmation. This was the first physical evidence that gravitational waves exist. Einstein had predicted them in 1916, but for decades, the idea had remained purely theoretical. The Hulse-Taylor binary changed that, and in 1993, Russell Hulse and Joseph Taylor were awarded the Nobel Prize in Physics. But the story of pulsars and gravitational waves was far from over. In June of 2023, 4 independent pulsar timing array collaborations from around the world, NanoGrav in North America, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array, simultaneously announced extraordinary results. After 15 or more years of meticulously timing dozens of the most stable millisecond pulsars in the galaxy, they had found compelling evidence for a gravitational wave background, a constant, low-frequency hum of gravitational radiation permeating the entire cosmos. This hum, with wave periods stretching over years to decades, is most likely produced by the accumulated signal from hundreds of thousands of pairs of supermassive black holes, each containing billions of solar masses, orbiting each other at the centers of merged galaxies across the universe. To detect this signal, scientists had essentially transformed our corner of the Milky Way into a gravitational wave detector the size of a galaxy. Using pulsars as the endpoints, the NanoGrav collaboration alone monitored 68 millisecond pulsars using data from the Arecibo Observatory, the Green Bank Telescope, and the Very Large Array. By correlating the tiny timing variations of thousands of pulsar pairs, they extracted the distinctive signature of gravitational waves from the noise. This detection opened an entirely new window on the universe, one that is sensitive to the mergers of the most massive black holes in existence, processes that shaped the evolution of galaxies over billions of years. And it was made possible entirely because millisecond pulsars are the most precise clocks in the universe. Extremes of nature, magnetars, starquakes, glitches, and zombie worlds, the universe, it turns out, has a flair for the extreme. And among the wide extreme varieties of neutron stars, perhaps none are more terrifying than magnetars. While a typical pulsar has a magnetic field roughly 1 trillion times stronger than Earth's, there exists a small subclass of neutron stars whose magnetic fields are roughly 1,000 times stronger still. These are the magnetars, and they possess the most powerful magnetic fields of any known objects in the universe. The existence of magnetars was proposed in 1992 by physicists Robert Duncan and Christopher Thompson, who theorized that a dynamo effect during the first seconds after a supernova could amplify the neutron star's magnetic field to staggering values. A magnetar's field can reach a quadrillion Gauss, more than 100 million times stronger than the most powerful magnets ever built in a laboratory. At these field strengths, the laws of physics themselves seem to bend. The magnetic field can polarize the vacuum of space, causing the vacuum itself to become birefringent, meaning light passing through it splits into two beams. The field forces atoms into thin, elongated cylinders. It deforms and stresses the solid crust of the neutron star, building up mechanical tension like a compressed spring. And when that tension is released, the consequences are violent. The most spectacular magnetar event ever recorded came from SGR 18-6-20, a magnetar located roughly 50,000 light-years away on the far side of the Milky Way on December 27, 2004. This magnetar's crust fractured in a massive starquake, and the resulting burst of gamma rays was beyond anything astronomers had ever witnessed. In 0.2 of a second, the magnetar released more energy than our sun produces in 250,000 years. The blast, despite originating halfway across the galaxy, was powerful enough to measurably compress Earth's ionosphere. Fishermen near the Arctic reportedly saw a sudden aurora. The burst briefly outshone the full moon in gamma rays. It was roughly 100 times more powerful than any previously observed magnetar flare. If SGR 18-6-20 were located within about 10 light-years of Earth, the consequences would be catastrophic. The radiation would strip our ozone layer and trigger a mass extinction. Fortunately, the nearest known magnetar is about 9,000 light-years away. But with an estimated 30 million or more dead magnetars drifting through the Milky Way, the possibility, however remote, that one might someday drift close enough to threaten Earth adds a sobering footnote to the magnetar story. Magnetars also helped solve one of astronomy's most persistent recent mysteries. Since 2007, astronomers had been detecting fast radio bursts, intense flashes of radio energy lasting only milliseconds, but releasing as much energy as the sun does in days. Their origin was completely unknown. Then, in April of 2020, the galactic magnetar SGR 1935+2154 emitted a burst strikingly similar to the extragalactic fast radio bursts, strongly suggesting that magnetars are responsible for at least some of these enigmatic signals. Beyond magnetars, the interiors of ordinary pulsars have also proven to be sources of profound mystery. Pulsars are supposed to be the most reliable clocks in nature, their spin rates decreasing gradually and predictably, but occasionally, without warning, a pulsar will suddenly speed up. Its rotation rate will jump by a tiny but measurable amount, as if the star were kicked. These events are called glitches, and they provide one of the only ways to probe the bizarre interior of a neutron star. The Vela pulsar, located about 1,000 light-years away and spinning roughly 11 times per second, is the most prolific glitcher known, experiencing a detectable glitch about once every 3 years. The leading explanation involves the superfluid neutrons in the neutron star's interior. Beneath the solid crust, the neutrons exist in a frictionless superfluid state. As the crust slows down due to magnetic braking, the superfluid continues spinning at its original rate. A lag develops between the two, and when the lag becomes too great angular momentum is suddenly transferred from the superfluid to the crust, causing the crust to jump to a higher rotation rate. Analysis of a 2016 Vela glitch revealed that the neutron star's interior appears to consist of at least 3 distinct rotating components, giving astronomers their first detailed map of the layered internal structure of one of these extraordinary objects. And then there are the pulsar planets, perhaps the most unexpected discovery of all. In 1992, astronomers Alexander Walskson and Dale Frail announced they had found planets orbiting a pulsar, not a normal star, but a millisecond pulsar designated PSR Bone 1257+12, located roughly 2,300 light-years away. The planets were detected through exquisitely tiny variations in the pulsar's timing, caused by the gravitational tug of the orbiting bodies. The system contains at least 3 planets, including 2 super-Earths, and a body barely twice the mass of our moon. These were the first confirmed exoplanets ever discovered, predating the famous detection of 51 Pegasi b by 3 years. In a supreme irony, the first worlds humanity ever found beyond our solar system were orbiting not a life-giving star like our sun, but the irradiated, compressed corpse of a star that died in a catastrophic explosion. The planets themselves were likely formed from debris left behind by a stellar merger. Truly, zombie worlds built from the ashes of stellar death. Their names, assigned in 2015, Draugr, Poltergeist, and Phobter, are fittingly drawn from mythological traditions of the undead and the terrifying. Everything we have discussed so far, the magnetic fields, the rotation, the glitches, the gravitational wave detection, depends on the physical nature of matter inside a neutron star. And the truth is, the interior of a neutron star remains one of the greatest unsolved puzzles in all of physics. No laboratory on Earth can recreate the conditions that exist inside these objects, and our theoretical understanding is incomplete. But what we do know, or strongly suspect, is fascinating enough to make the imagination real. The outer crust, extending perhaps a kilometer below the surface, is a rigid lattice of iron and other heavy nuclei, threaded by a sea of free electrons. This crust is extraordinarily hard, far harder than diamond. And the immense surface gravity means that the largest possible irregularity, the tallest mountain on a neutron star, would measure perhaps a centimeter or 2. Everything is crushed flat. Below this, in the inner crust, the pressure is so extreme that the nuclei begin to lose their identity. They are crushed and deformed into exotic structures that physicists, with a flair for culinary metaphor, have named nuclear pasta. At the top of this region, matter forms into spherical blobs called gnocchi. Deeper, the blobs are crushed into long rods, the spaghetti phase. Deeper still, the rods are flattened into broad sheets, the lasagna phase. These exotic arrangements exist at the boundary between ordinary nuclear matter and the pure neutron fluid of the core. And computer simulations suggest that nuclear pasta may be the strongest material in the entire universe, roughly 10 billion times stronger than steel. In the outer core, below the crust, the matter is predominantly a superfluid of neutrons, with a small fraction of protons forming a superconducting fluid and electrons providing charge neutrality. The superfluid rotates by forming an array of quantized vortices, tiny whirlpools of circulating neutron fluid. And it is the dynamics of these vortices, their interaction with the solid crust, that is thought to be responsible for pulsar glitches. And at the very center, in the inner core, lies territory unknown. The density here exceeds anything found in ordinary atomic nuclei. And what happens to matter under such conditions is simply not known with certainty. Some theories suggest that the neutrons break apart into their constituent quarks and gluons, forming a quark-gluon plasma. Others propose the creation of exotic particles called hyperons, or strange quark matter, or condensates of kaons and pions, or phases of matter that have no name because they have never been conceived. Determining which of these possibilities is correct, or whether the answer is something entirely different, is one of the great quests of modern physics. Every measurement of a neutron star's mass, radius, or behavior is a clue that helps constrain the possibilities. The future, new eyes on the cosmos and the endless beat, the story of pulsars, now approaching its 7th decade, shows no sign of winding down. If anything, we stand at the threshold of a new era. The 500-meter aperture spherical telescope, FAST, in China's Guizhou province, has already discovered over 1,000 pulsars since it began operating, including hundreds from its galactic plane pulsar snapshot survey alone. This telescope is so sensitive that it can detect pulsars too faint for any other instrument on Earth. And it has already increased the number of known millisecond pulsars by roughly 10%. The survey is still less than a quarter complete. The square kilometer array, currently under construction across sites in South Africa and Western Australia, promises to be roughly 50 times more sensitive than any existing radio telescope. It is expected to discover tens of thousands of new pulsars when it comes fully online, potentially finding the long-sought pulsar orbiting Sagittarius A star, the supermassive black hole at the center of our galaxy. Such a discovery would provide the ultimate test of general relativity in the strongest gravitational field the Milky Way has to offer. The pulsar timing arrays that detected the gravitational wave background in 2023 are still collecting data. And with every passing year, the signal becomes clearer as more millisecond pulsars are added to the arrays and observation baselines grow longer. Scientists expect to resolve individual supermassive black hole binaries, mapping the gravitational wave sky with increasing precision. This new window on the cosmos will reveal the history of galactic mergers across cosmic time, probing the evolution of the universe's largest structures. Pulsars have even been proposed as navigational beacons for future interstellar travel because millisecond pulsars are distributed throughout the galaxy, and each has a unique pulse signature. A spacecraft could, in principle, triangulate its position by timing the signals from several known pulsars. Much like the Global Positioning System uses satellite signals, NASA has already tested this concept with an experiment called Sextant aboard the International Space Station, using X-ray pulsar signals to autonomously determine the station's position. Future missions to Mars and beyond might rely on pulsar navigation to determine their locations without depending on communication with Earth. In a profound sense, pulsars embody one of the most beautiful paradoxes in all of nature. They are the remnants of destruction, the the compressed corpses of stars that died in the most violent explosions the universe can produce. And yet, from that destruction comes something of extraordinary beauty and utility: a perfect clock, a gravitational wave detector, a laboratory for extreme physics, a beacon that shines across the galaxy with mechanical precision for billions of years. Every pulse that reaches Earth from a distant neutron star carries information encoded not by any intelligence, but by the laws of physics themselves. It carries information about the rotation rate of the star, about the density and turbulence of the interstellar medium it passed through on its journey to us, about the gravitational fields it encountered along the way, about the warping of spacetime by passing gravitational waves. Each pulse is a tiny package of data, launched from the magnetic poles of a dead star and sent hurtling across hundreds or thousands of light years of empty space, arriving at our telescopes with a regularity that would make a Swiss watchmaker weep with envy. And we have barely begun to exploit what pulsars can teach us. The more than 3,700 pulsars discovered to date represent only a thin slice of the estimated population. Models suggest that as many as 1.1 million detectable pulsars may exist in our galaxy alone. And with the next generation of radio telescopes coming online, we are poised to discover tens of thousands more. Each new pulsar is a potential new laboratory, a new data point in our quest to understand the fundamental nature of matter and gravity and spacetime. But before we close this chapter, there are threads we have touched on that deserve to be woven together more fully. We have talked about individual discoveries and individual types of pulsars, but the deeper story is about how all of these threads connect, how pulsars sit at the intersection of nearly every major question in modern astrophysics. The double pulsar, nature's perfect laboratory. Among the thousands of known pulsars, one system stands above nearly all others in its scientific value. The double pulsar, PSR J700 and 37-3039, discovered in 2003 by a team led by Marta Burgay, using the Parkes radio telescope in Australia. This system is extraordinary because both neutron stars and the binary are visible as pulsars. One spins roughly 23 milliseconds per rotation, the other about 2.8 seconds. The two stars orbit each other in just 2 hours and 27 minutes, one of the tightest known binary pulsar orbits, and they will merge in about 85 million years, making this system one of the best candidates for a future gravitational wave detection by ground-based observatories. The double pulsar is the most relativistic binary system known. The orbital velocities are higher, the gravitational fields stronger, and the relativistic effects more pronounced than in any other known binary pulsar, including the famous Hulse-Taylor system. The system has allowed physicists to measure no fewer than 7 distinct relativistic effects, including the advance of periastron, gravitational redshift, Shapiro delay, orbital period, decay, due to gravitational wave emission, geodetic precession, and even the ratio of the two stars' masses derived purely from relativistic spin-orbit coupling. Every single one of these measurements agrees with the predictions of general relativity to extraordinary precision. The most stringent test, from the Shapiro delay measurement, confirms Einstein's theory to within 0.005 of a percent. But the double pulsar offers something even more remarkable. Because both stars are pulsars, and because the faster pulsar's beam happens to pass behind the slower pulsar as seen from Earth, astronomers can observe the eclipses of one pulsar by the magnetosphere of the other. These eclipses provide direct information about the size, shape, and structure of the slower pulsar's magnetosphere, something that cannot be studied in any other way. The eclipses reveal that the magnetosphere has a complex, three-dimensional structure that varies as the pulsar rotates, and the duration and depth of the eclipses change over time due to geodetic precession. The relativistic wobble of the slower pulsar's spin axis, caused by the gravitational influence of its companion. In 2021, a comprehensive analysis of 16 years of timing data from the double pulsar was published, representing one of the most thorough tests of general relativity ever conducted. The paper, involving dozens of researchers from institutions around the world, reported measurements of all 7 relativistic effects and found complete consistency with Einstein's predictions. No alternative theory of gravity tested against the data could match this performance. The double pulsar remains, to this day, the single most powerful laboratory for testing gravitational physics in the strong field regime. The discovery of the double pulsar also had implications far beyond testing relativity. By measuring the masses of both stars with high precision, approximately 1.34 and 1.25 solar masses, the system provided important constraints on the equation of state of dense matter and on the evolutionary pathways that produce close binary neutron star systems. The existence of such a tight binary, with both stars visible as pulsars, is itself a remarkable stroke of luck, since the probability of both beams crossing our line of sight simultaneously is very small. The discovery underscored the importance of wide-area pulsar surveys and the value of persistence in astronomical observation. Pulsar wind nebulae. The breath of dead stars. When a pulsar spins, it does not just emit beams of radiation from its poles. It also drives a relentless wind of charged particles outward into its surroundings at nearly the speed of light. This pulsar wind, composed primarily of electrons and positrons, accelerated by the rotating magnetic field, carries enormous energy and slams into the surrounding material. Whether that material is the expanding debris of the supernova that created the pulsar or the ambient interstellar medium, the result is a pulsar wind nebula, a bubble of high-energy particles and magnetic fields inflated by the pulsar's wind within the larger structure of the supernova remnant. The Crab Nebula is the most famous example, but it is far from the only one. Dozens of pulsar wind nebulae are known, each one shaped by the interplay between the pulsar's wind, the pressure of the surrounding supernova remnant, and the motion of the pulsar through space. Pulsar wind nebulae are among the most efficient particle accelerators in the universe. The electrons and positrons in the wind are accelerated to energies that dwarf anything achievable in human-built accelerators. The Large Hadron Collider, the most powerful accelerator on Earth, can accelerate protons to energies of about 7 trillion electron volts. The particles in pulsar wind Nebulae routinely reach energies of 1,000 trillion electron volts and beyond, 100 times higher. These ultra-high energy particles produce radiation across the electromagnetic spectrum, from radio waves through X-rays to the most energetic gamma rays ever detected. In recent years, ground-based gamma-ray observatories like HESS, MAGIC, and VERITAS have detected pulsar wind nebulae at energies exceeding 100 trillion electron volts, revealing the incredible efficiency with which pulsars convert their rotational energy into particle acceleration. The study of these nebulae provides insights into the physics of particle acceleration in extreme environments, the structure of relativistic shock waves, and the mechanisms by which energy is transferred from rotating magnetic fields to fast-moving particles. These processes are relevant not just to pulsars, but to a wide range of astrophysical phenomena, from the jets of active galactic nuclei to the acceleration of cosmic rays. The shapes of pulsar wind nebulae are also beautiful and distinctive. Many display a characteristic structure with a bright, compact region near the pulsar, called the wind termination shock, surrounded by a more diffuse halo of emission. Some show jets and equatorial outflows that trace the geometry of the pulsar's rotation axis and magnetic field. The Vela pulsar, for example, drives a spectacular jet of particles that has been observed to wobble back and forth over time, possibly due to precession of the pulsar's spin axis. These observations provide information about the internal structure and dynamics of the neutron star that is impossible to obtain by any other means. Pulsar wind nebulae also serve as cosmic particle factories, injecting high-energy electrons and positrons into the interstellar medium. These particles contribute to the overall population of cosmic rays, the high-energy particles that constantly bombard the Earth from all directions. Some scientists have suggested that nearby pulsars, through their wind nebulae, could be responsible for an observed excess of cosmic ray positrons detected by experiments like PAMELA and the Alpha Magnetic Spectrometer on the International Space Station. If true, this would mean that dead stars are still actively influencing the environment of our solar system, billions of years after they died, their energetic breath reaching us across the light years. The interplay between pulsars and their environments is a microcosm of one of the deepest themes in astrophysics: the cycle of matter and energy that connects stars to the interstellar medium to new generations of stars. Massive stars are born from clouds of gas and dust, live out their lives fusing lighter elements into heavier ones, die in supernova explosions that scatter those elements into space, and leave behind neutron stars that continue to pump energy into their surroundings for millions of years after the explosion. The material expelled by supernovae, enriched with heavy elements and energized by pulsar winds, eventually mixes back into the interstellar medium and is incorporated into new clouds, new stars, new planets. It is a cycle as old as the galaxy itself, and pulsars play a central role in keeping it running. Consider, for a moment, the sheer range of physics that pulsars touch. Start with nuclear physics. The interior of a neutron star is essentially a giant atomic nucleus, roughly 20 kilometers across instead of a few femtometers. Understanding what happens inside a neutron star requires understanding the behavior of nuclear matter at densities that cannot be achieved in any terrestrial experiment. The most powerful particle accelerators on Earth, facilities like the Large Hadron Collider at CERN and the relativistic Heavy Ion Collider at Brookhaven National Laboratory, can briefly create tiny droplets of quark-gluon plasma by smashing heavy nuclei together at nearly the speed of light. But these droplets are unimaginably small and vanish in a fraction of a trillionth of a second. A neutron star, by contrast, maintains extreme density conditions continuously for billions of years. It is nature's own nuclear physics experiment, running on a scale and for a duration that no human facility could ever match. Every measurement of a neutron star's mass or radius constrains the equation of state of dense nuclear matter, the mathematical relationship that describes how pressure relates to density inside these objects. Different theoretical models predict different equations of state, and each model leads to different predictions for the maximum mass a neutron star can achieve, the minimum radius it can have, and the nature of the matter at its core. By measuring pulsar masses in binary systems, something that can be done with extraordinary precision thanks to the regularity of pulsar timing, astronomers can rule out models that predict masses inconsistent with observations. The most massive neutron star yet measured, PSR J700 and 40 plus 6620, tips the scales at roughly 2.1 solar mass, a value that already rules out several popular models for the equation of state, and strongly constrains what kinds of exotic matter can exist at the highest densities. Now consider general relativity. Pulsars have been Einstein's best friend and most rigorous examiner for decades. The Hull-Staler binary provided the first evidence for gravitational waves. The double pulsar system, PSR J700, and 37-3039, discovered in 2003, is even more remarkable because both neutron stars in the system are detectable as pulsars. This system has allowed tests of general relativity that are at least 5 times more precise than anything the Hull-Staler binary could provide. The orbital precession, time dilation, gravitational redshift, and orbital decay of this system all match Einstein's predictions with breathtaking accuracy, confirming general relativity in the strong field regime, where the theory has the most to say, and where alternatives to Einstein's theory make their most divergent predictions. The pulsar timing arrays push the testing of gravity into an entirely different arena. By monitoring the arrival times of pulses from dozens of millisecond pulsars spread across the sky, these arrays are sensitive to gravitational waves with wavelengths measured in light years, waves that oscillate on timescales of years to decades. The gravitational wave background detected in 2023 by NanoGrav and its partner collaborations is believed to be generated primarily by the orbital motions of supermassive black hole binaries, each pair containing 2 black holes with masses measured in the billions of solar masses. These are the largest gravitational wave sources in the universe, and they produce signals that no ground-based detector like LIGO could ever hope to see, because the wavelengths are simply too long. only a detector the size of the galaxy, built from an array of the universe's most precise natural clocks, could pick up this cosmic hum. Pulsars are that detector. Then there is plasma physics and magnetohydrodynamics. The magnetosphere of a pulsar is one of the most extreme plasma environments in the known universe. Particle densities, electric field strengths, and magnetic field configurations in the pulsar magnetosphere reach values that cannot be reproduced in any laboratory. The details of how pulsars actually generate their radio emission, the specific physical mechanism by which the rotating magnetic field converts rotational energy into coherent radio waves, remain one of the oldest and most persistent unsolved problems in astrophysics. We have known about pulsars for nearly 60 years, and we still do not have a complete first principles understanding of how they shine. The problem is fiendishly difficult because it requires solving coupled equations of electrodynamics and plasma physics in the rotating frame of a rapidly spinning, strongly magnetized neutron star, a mathematical challenge of the highest order. Computer simulations of pulsar magnetospheres have made tremendous progress in recent years, enabled by advances in computational power and numerical methods. These simulations, sometimes called pulsars in a box, trace the paths of charged particles through the electric and magnetic fields near the neutron star, revealing complex patterns of current flow and radiation that are gradually bringing the theoretical picture into alignment with observations. But there is still a gap between the simulated and the observed, and closing that gap will require both better simulations and better observational data from the next generation of telescopes. Pulsars also connect to condensed matter physics in unexpected ways. The interior of a neutron star is thought to contain superfluid neutrons and superconducting protons, quantum mechanical states of matter that are normally associated with laboratory conditions near absolute zero. In a neutron star, these states exist at temperatures of millions of degrees, sustained not by low temperatures, but by the extreme densities that make the quantum mechanical pairing of neutrons energetically favorable, even in the face of tremendous thermal energy. The study of superfluidity and superconductivity in neutron stars is a direct extension of the same physics that governs superconducting magnets in MRI machines and particle accelerators. But operating under conditions so extreme that the behavior of matter may be qualitatively different from anything observed on Earth. Pulsar glitches, those sudden spin-ups that we discussed earlier, are the most direct observational probe of superfluidity inside neutron stars. The size, frequency, and recovery behavior of glitches contain information about the fraction of the star's moment of inertia that is stored in the superfluid component, about the strength of the coupling between the superfluid and the solid crust, and about the mechanisms by which angular momentum is transferred between different internal components. Detailed studies of Vela pulsar glitches have already provided estimates of the neutron star's mass and constraints on the superfluid pairing gap, quantities that are directly relevant to fundamental nuclear physics. And finally, pulsars connect to the grandest questions in cosmology. The gravitational wave background detected by pulsar timing arrays carries information about the assembly history of the universe's largest structures. Galaxies grow through mergers. And when two galaxies merge, the supermassive black holes at their centers are expected to eventually sink to the center of the merged galaxy and form a binary, spiraling together over millions of years while emitting gravitational waves. The spectrum and amplitude of the gravitational wave background encode information about how often galaxies have merged throughout cosmic history, how massive their central black holes are, and how efficiently those black holes find each other and form binaries. By characterizing this background with increasing precision over the coming decades, pulsar timing arrays will provide a new window on the growth and evolution of cosmic structure, complementing observations from optical and infrared telescopes. Some theorists have even proposed that the gravitational wave background could contain contributions from exotic cosmological sources, such as cosmic strings, hypothetical one-dimensional defects in the fabric of spacetime that might have formed in the first fractions of a second after the Big Bang. If cosmic strings exist and contribute to the gravitational wave background, pulsar timing arrays might be able to detect their signature, providing evidence for new physics beyond the standard model of particle physics and standard cosmological models. The stakes could not be higher. The Joy Division connection, pulsars in culture. It would be a shame to discuss pulsars without mentioning one of the most unexpected places their influence has been felt: the cover of an album by the English post-punk band Joy Division. The iconic cover of their 1979 debut album, Unknown Pleasures, features a stark black and white image of stacked waveforms that look like a mountain range of radio signals. This image was traced by Scientific American's graphics editor to its origins. It is a plot of successive radio pulses from the first pulsar ever discovered, CP 1919, the very same source that Jocelyn Bell detected in 1967. The plot was created in 1970 by Harold Kraft, a graduate student at the Arecibo Observatory in Puerto Rico. As part of his doctoral thesis on pulsar emission, the image made its way from Kraft's thesis into the Cambridge Encyclopedia of Astronomy, where it was spotted by Peter Saville, the graphic designer for the Factory Records label. Saville, struck by the beauty and mystery of the waveforms, adapted them for the album cover without any idea what they represented. The result became one of the most recognizable and widely reproduced images in the history of popular music. Printed on countless t-shirts, posters, tattoos, and merchandise over the decades, it is a beautiful irony that the signal from a dead star, detected by a graduate student who was not awarded the Nobel Prize for her discovery, became an enduring symbol of a band whose lead singer, Ian Curtis, died tragically young. Pulsars, it seems, have a way of leaving their mark on culture as well as science. How many pulsars are out there? As of the mid-2020s, more than 3,700 pulsars have been cataloged by astronomers. This number has been growing rapidly in recent years, driven largely by the extraordinary sensitivity of the FAST telescope in China, which has discovered over 1,000 pulsars from all its surveys combined. The FAST Galactic Plane Pulsar Snapshot survey alone has found more than 750 new pulsars, with only about a quarter of its planned survey area completed. When the full survey is done, the total could reach into the thousands from this single project. But the known pulsars are only the tip of the iceberg. Population models suggest that the Milky Way contains roughly 1 billion neutron stars in total, of which perhaps 1.1 million could be detectable as pulsars if we had sensitive enough telescopes pointed in the right direction. The vast majority of these remain undiscovered, either because they are too faint for current instruments, because their beams do not cross our line of sight, or because they are obscured by the dense clouds of gas and dust that fill the galactic plane. The Square Kilometer Array, expected to begin full scientific operations in the late 2020s, will revolutionize pulsar surveys. With its enormous collecting area and advanced digital signal processing, the SCA is expected to discover up to 30,000 new pulsars, roughly 10 times the current total. Among these will likely be rare and exotic systems. Pulsars in binary orbits around black holes, pulsars in the crowded environment of the galactic center, extremely fast millisecond pulsars that push the theoretical limits of neutron star structure, and perhaps entirely new categories of pulsating neutron stars that we have not yet imagined. The Chinese Fast Telescope and the CHIME Telescope in Canada are also contributing to this explosion of discovery. CHIME, the Canadian Hydrogen Intensity Mapping Experiment, is a novel radio telescope that monitors a large swath of the northern sky every day. Its CHAMPSS survey, the CHIME All-Sky Multi-Day Pulsar Stacking Search, has already begun discovering new pulsars by stacking together observations taken over many days, a technique that allows it to detect pulsars that are too faint to be seen in a single observation. This approach is particularly well suited to finding pulsars with unusual emission properties, such as those that only emit sporadically, and it may reveal an entirely new population of sources that have been missed by traditional surveys. The Arecibo Observatory in Puerto Rico, which for decades was the world's most powerful radio telescope and the birthplace of many landmark pulsar discoveries, collapsed in December of 2020 when its 900-ton instrument platform crashed into the 300-meter dish below. The loss of Arecibo was a devastating blow to pulsar science, but the data it collected over more than 50 years of operation continues to yield new discoveries. As recently as 2025, analysis of archival Arecibo data led to the discovery of 18 previously unknown pulsars, and researchers estimate that many more remain hidden in the unprocessed portion of the survey data. Each new pulsar discovery adds to our understanding. Every millisecond pulsar is a potential addition to pulsar timing arrays, increasing their sensitivity to gravitational waves. Every young pulsar in a supernova remnant tells us something about how neutron stars are born. Every glitching pulsar reveals something about the superfluid interior. Every binary pulsar provides a new test of general relativity. The more pulsars we find, the more precisely we can answer the deepest questions about the nature of matter, gravity, and the structure of the cosmos. There is something almost philosophical about the existence of pulsars in a universe that often seems chaotic and unpredictable, where stars are born and die, where galaxies collide and merge, where black holes swallow everything that comes too close. Pulsars stand as monuments to order and precision. They are the universe's metronomes, beating out a rhythm that persists for millions or billions of years, undisturbed by the tumult around them. Consider the journey of a single pulse. It begins at the magnetic pole of a neutron star, a region no larger than a football field, where particles are accelerated to nearly the speed of light by electric fields strong enough to tear atoms apart. The pulse is emitted as a beam of radio waves, coherent and focused, launched into the void. It travels outward at the speed of light, passing through the magnetosphere of the neutron star, then through the interstellar medium, a thin soup of gas, dust, and free electrons that fills the space between the stars. As it passes through this medium, the pulse is slightly dispersed, with higher frequency components arriving before lower frequency ones. Because the interstellar medium is a plasma and acts as a frequency-dependent lens, the amount of dispersion tells us how much plasma the pulse passed through, which in turn tells us how far away the pulsar is. After traveling for perhaps 1,000 years, perhaps 10,000 years, the pulse arrives at Earth. It has crossed a gulf of space so vast that the light from the sun, which reaches Earth in about 8 minutes, would take years or millennia to cover the same distance. The pulse is faint, incredibly faint, perhaps carrying only a few trillionths of a watt of power by the time it reaches our planet, but it arrives at exactly the predicted time, to within a millionth of a second. It carries within its timing the signature of the neutron star that created it, the fingerprint of the interstellar medium it passed through, and possibly the faint imprint of gravitational waves that stretched the space-time between the pulsar and Earth. This single pulse, this whisper from a dead star, is one of trillions that the pulsar has emitted over its lifetime. And it tells a story that spans nearly every corner of fundamental physics. Pulsars remind us that the universe is not just vast and violent and strange. It is also precise. It keeps time. It follows rules. And sometimes, if we are paying close attention, if we are willing to look at 400 feet of chart paper a day and flag a quarter-inch anomaly with a question mark, the universe reveals its secrets. Right now, as you sit here listening to these words, thousands of pulsars are beaming their signals across the Milky Way. Some have been spinning since before our solar system coalesced from a cloud of gas and dust 4.5 billion years ago. Some were created in explosions witnessed by medieval astronomers on the other side of the world. Some were resurrected from near death by matter stolen from doomed companion stars, spun back up to dizzying speeds by a process that took longer than the entire history of complex life on Earth. And all of them are beating with a rhythm so perfect, so unwavering, so immune to the chaos of the universe around them, that we have used it to hear the hum of space-time itself. They are the lighthouses of the universe, these spinning remnants of stellar death. And their light, pulsing with perfect rhythm through the endless dark, continues to guide us toward understanding. Right now, somewhere out there, a signal is traveling toward Earth from a pulsar we have not yet discovered. It has been traveling for a very long time. It carries information about the fabric of space-time, about the nature of matter under conditions we cannot replicate, about the behavior of gravity in regimes Einstein could only imagine. One day, a telescope will catch that signal. A graduate student, a computer algorithm, or a citizen scientist will notice something unusual in the data. And once again, a tiny anomaly will open a door to something vast. That is the story of pulsars. It is not finished. It may never be, because the deeper we look, the more we find. And the tools that pulsars provide, their precision timing, their extreme physics, their sensitivity to the most subtle distortions of spacetime, are only growing more powerful with each passing year and each new telescope that comes online. There are still fundamental questions that only pulsars can answer. Questions about the nature of the densest matter in the cosmos. Questions about the limits of Einstein's theory. Questions about the fate of the universe's largest structures and the gravitational waves that ripple between them. One of the most fundamental questions in all of physics is deceptively simple to state. What happens to matter when you squeeze it hard enough? Take a chunk of iron, compress it. At first, the atoms resist, held apart by the repulsion of their electron clouds. Push harder, and the crystal structure deforms. Push harder still, and the electrons are forced into the atomic nuclei, merging with protons to form neutrons. Push yet harder, and you enter a regime where our theories begin to struggle, where the distinction between individual particles begins to blur, where matter may exist in states that have never been observed in any laboratory and may never be. This question, the equation of state of dense matter, is not merely academic. It has concrete, observable consequences. The equation of state determines the maximum mass that a neutron star can achieve before collapsing into a black hole. It determines the minimum radius a neutron star can have. It determines whether the core of a neutron star contains ordinary neutron matter, a quark-gluon plasma, hyperons, kaon condensates, or something else entirely. And crucially, these properties are measurable. When two neutron stars collide, as was spectacularly observed for the first time by the LIGO and Virgo gravitational wave detectors in August of 2017, in an event designated G170,817. The gravitational wave signal encodes information about the internal structure of the colliding stars. The way the stars deform under each other's tidal influence in the last moments before merger depends directly on the equation of state. A stiff equation of state, where the pressure rises sharply with density, produces larger neutron stars that deform less. A soft equation of state, where the pressure rises more gently, produces smaller, more easily deformed stars. By analyzing the gravitational wave signal from the merger, physicists were able to place the first direct constraints on the equation of state from a gravitational wave observation. But pulsars contribute to this puzzle in their own distinct way. In binary pulsar systems, the exquisitely precise timing of pulsar signals allows astronomers to measure the masses of neutron stars with remarkable accuracy. These mass measurements serve as hard limits on the equation of state. Any model that cannot support a neutron star as massive as the most massive one observed is immediately ruled out. The discovery of neutron stars with masses above 2 solar masses, such as PSR J700 and 40 plus 6620, has already eliminated several popular models that predicted softer equations of state and lower maximum masses. radius measurements are harder, but equally important. The Neutron Star Interior Composition Explorer, known as NICER, is an X-ray telescope mounted on the International Space Station that is specifically designed to measure the sizes of neutron stars. NICER does this by observing the X-ray emission from hot spots on the neutron star's surface, the same hot spots associated with the magnetic poles where pulsar beams originate. By analyzing how the brightness and shape of the X-ray pulses change as the star rotates, accounting for the extreme gravitational lensing that causes the star to appear larger than its physical size, because light from the backside is bent around by the intense gravity. NICER can infer the radius of the star. The results from NICER, combined with mass measurements from pulsar timing and constraints from gravitational wave observations, are gradually mapping out the equation of state of the densest matter in the universe. Each new data point narrows the range of possibilities. Each new measurement brings us closer to answering one of the oldest questions in physics. What does matter, really, when you push it to the absolute limit? This is a question that connects the smallest scales in nature, the interactions between quarks and gluons inside a proton, to the largest, the structure and evolution of neutron stars. It connects the physics of the first microseconds after the Big Bang, when quark-gluon plasma filled the entire universe, to the physics of the present day, where that same exotic state of matter may exist in the cores of neutron stars scattered throughout every galaxy. Pulsars are not just astronomical objects. They are bridges between the world of the very small and the world of the very large, between quantum mechanics and general relativity, between particle physics and cosmology. They sit at the crossroads of nearly every major frontier in modern physics. There is one more dimension to pulsars that is worth exploring, not because it is scientifically crucial, but because it captures something about the wonder of these objects that dry numbers alone cannot convey. Pulsars make sound. Not literally, of course, since space is a vacuum and sound cannot travel through it. But the radio pulses that pulsars emit can be converted into audio signals by simply feeding the radio data into a speaker, and the result is haunting. A slow pulsar, spinning once every second or so, sounds like a steady, resonant drumbeat, a deep, rhythmic thudding that evokes the heartbeat of some vast, unseen creature. Speed up the rotation, and the sound rises in pitch. A pulsar spinning 10 times a second sounds like a rapid, percussive rattle. A millisecond pulsar spinning hundreds of times per second produces a buzz, a hum, an insect-like whine that seems too rapid, too precise, too mechanical to be produced by any natural process. And yet it is entirely natural. The sound of angular momentum and magnetic fields, and the conservation laws of physics playing out on a stage 12 miles across. The Crab pulsar, spinning 30 times a second, produces a sound in the audio range that has been described as a low, resonant buzz. Listening to it feels like holding a stethoscope to the chest of the universe and hearing its heartbeat. It is a reminder that the cosmos is not silent. It is full of rhythms, from the 3-minute oscillations of the sun to the orbital periods of planets to the nanosecond pulses of millisecond pulsars. The universe keeps time in ways that we are only beginning to appreciate. when the largest starquake ever recorded rattled the magnetar SGR 18 6-20 in 2004. The resulting vibrations of the neutron star's crust produced oscillations in its X-ray emission at a frequency of 94.5 Hz. This is close to the frequency of the 22nd key on a piano, an F sharp. A dead star, 50,000 light-years away, was ringing like a bell, and the note it sang was one that any musician could play. If that is not poetry written in the language of physics, it is hard to know what would be the loneliest objects. Isolated neutron stars and the Magnificent Seven. Not all neutron stars are pulsars, and not all of them have companions. Some are utterly alone, drifting through the galaxy in total isolation, too old to pulse, too cold to accrete, too dim to see by any conventional means. These objects are essentially invisible, detectable only if they happen to pass through a region of interstellar gas, dense enough that the captured material heats up and produces faint X-ray emission, or if their residual thermal glow from their supernova birth is still barely detectable. In the 1990s, a small group of nearby isolated neutron stars was discovered by the ROSAT X-ray satellite. These objects, 7 in total, became known as the Magnificent Seven. They are remarkable for what they are not. They are not pulsars in the traditional sense. They do not produce the powerful radio beams characteristic of young, rapidly spinning neutron stars. They are not in binary systems. They are not magnetars. They are simply very nearby, relatively young neutron stars that are still hot enough from their formation, a few 100,000 to 1,000,000 years ago, to emit detectable thermal X-rays. The Magnificent Seven provide a unique opportunity to study neutron stars in their simplest form, without the complications of accretion, strong magnetic emission, or binary interactions. By measuring their surface temperatures and comparing them to theoretical cooling models, astronomers can constrain the neutrino emission processes operating in their cores, which in turn provides information about the composition and equation of state of their interiors. Some of the 7 have measured temperatures that are higher than expected for their ages, which could indicate the presence of exotic heating mechanisms, or could point to unusual internal compositions. These lonely wanderers also remind us of the sheer number of neutron stars in the galaxy. If 7 neutron stars happen to be close enough to Earth and young enough to be detectably warm, then the total population of neutron stars in the Milky Way must be enormous. Estimates place the number at roughly 1 billion, most of them ancient, cold, dark, and utterly undetectable with current technology. They are the silent majority of the neutron star population, the ghosts of stars that died long ago, drifting through the galaxy like embers from a fire that burned out eons past, navigating by dead stars. The pulsar GPS. The idea of using pulsars for navigation sounds like science fiction, but it is quickly becoming science fact. The concept is elegant in its simplicity. Millisecond pulsars, with their extraordinarily stable rotation rates and their unique pulse profiles, are effectively cosmic beacons with known positions and known timing signatures. A spacecraft equipped with an X-ray detector, sensitive enough to pick up the pulses from several known millisecond pulsars, could, in principle, determine its own position in 3-dimensional space. by comparing the observed arrival times of the pulses to the predicted arrival times based on the spacecraft's assumed position. The discrepancies between observed and predicted times reveal how far the spacecraft has drifted from its assumed location, allowing it to correct its navigation autonomously without any communication with Earth. This technique, known as X-ray pulsar navigation, or XNAV, was successfully demonstrated in 2017 by NASA's Station Explorer for X-ray timing and navigation technology experiment, known as Sextant, using data from the NICER X-ray telescope on the International Space Station. The Sextant team showed that they could determine the station's position to within about 5 kilometers using pulsar timing alone. While 5 kilometers is not yet competitive with GPS for Earth-orbiting spacecraft, the technology is in its infancy. And for deep space missions far from Earth, where GPS signals are unavailable and communication delays with ground controllers can stretch to hours, pulsar navigation could become indispensable. Imagine a crewed mission to Mars, or an unmanned probe heading for the outer solar system that can determine its own position by listening to the steady beats of dead stars scattered across the galaxy. No ground control needed, no communication delay. Just the ancient, reliable pulse of neutron stars that have been keeping time since before the dinosaurs walked the Earth, serving as guideposts for humanity's first tentative steps beyond our home world. The dead stars of the Milky Way, it turns out, may light the way for the living. It is a fitting role for pulsars, these remnants of stellar death transformed into tools for exploration and discovery in a universe where nothing lasts forever, where even stars are born, burn, and die. Pulsars represent a kind of afterlife, a way for a dead star to continue contributing to the story of the cosmos long after its nuclear fires have gone out. They are proof that in the universe, death is not the end. It is a transformation, a change of state, a new beginning. We have traveled a long road in this exploration of pulsars, from a muddy field in Cambridge to the hearts of supernova remnants, from the surfaces of magnetars to the superfluid interiors of glitching neutron stars, from the discovery of the first exoplanets to the detection of a gravitational wave background that hums through the fabric of spacetime. Along the way, we have met some extraordinary people. Jocelyn Bell, who noticed what others missed and changed astronomy forever. Anthony Hewish, who built the telescope that made the discovery possible. Russell Hulse and Joseph Taylor, who found a binary pulsar and used it to prove that gravitational waves are real. Thomas Gold and Franco Passini, who figured out what pulsars actually are before anyone had a chance to be confused for too long. Alexander Walskson and Dale Frail, who discovered zombie planets orbiting a dead star and opened the era of exoplanet science 3 years before anyone found a planet around a normal star. And we have met some extraordinary objects. The Crab pulsar, born in an explosion witnessed by Chinese astronomers in 1054, is still powering the nebula that bears its name after nearly a millennium. PSR J1748-2446 AD, spinning 716 times per second. Its equator moving at a quarter of the speed of light. The Hulse-Taylor binary, its orbit decaying at precisely the rate predicted by Einstein, is destined to merge in a cataclysmic collision 300 million years from now. SGR 18 6-20. The magnetar whose starquake sent a blast of gamma rays that briefly outshone the full moon from 50,000 light-years away. The Vela pulsar, whose glitches revealed 3 distinct rotating layers inside its superfluid interior. And PSR Bone 1257 plus 12, the pulsar around which humanity found its first planets beyond the solar system. Worlds named after myths of the undead. Each of these objects, each of these discoveries, is a chapter in a story that is still being written. New telescopes are coming online. New pulsars are being discovered every month. New gravitational wave signals are emerging from the noise of pulsar timing data. New theoretical models are being developed to explain the mysterious emission mechanisms, the exotic interior compositions, the violent starquakes, and the patient, persistent rhythm of these cosmic lighthouses. The universe is full of sound and fury, of explosions and collisions and catastrophes that reshape the cosmos on scales we can barely comprehend. But pulsars are something different. They are the quiet aftermath, the orderly remnant, the precise and patient signal that persists long after the violence of creation has subsided. They are proof that even in a universe of chaos, order endures, that even from the death of a star, something beautiful and useful and profoundly meaningful can emerge. That even the smallest signal, a quarter-inch of scruff on a paper chart, can open a window onto the deepest truths of nature. Right now, somewhere in the galaxy, a pulsar is spinning. It has been spinning for a very long time, and it will continue for a very long time to come. Its beams sweep across the cosmos like the arms of a clock marking time with a precision that humbles human engineering. And if you point a radio telescope in the right direction and listen carefully, you can hear it. A steady, rhythmic pulse arriving from across the void, as reliable as the sunrise and as old as the stars. That pulse is a message from the universe. Not a message with words or meaning in the human sense, but something perhaps more profound. A demonstration that the laws of physics are real, that they hold everywhere, that they can be understood, and that they produce wonders beyond anything we could have imagined before we first looked up at the sky and wondered what was out there. Pulsars are the lighthouses of the universe, and their light is still guiding us home. If you enjoyed this deep dive into the cosmos, please hit that like button and subscribe to the channel. Drop a comment below and tell us what you thought or what you would like us to cover next. Every like, every subscription, every comment helps us keep exploring the universe together. Thanks for watching, and we will see you next time.